Hello everyone, welcome to the second video of chapter number 4, Chemical Thermodynamics. In last video, we have studied few concepts of the thermodynamics, that is system, state variable, state function and processes. In this video, we are going to study work done in different processes and another very important concept, that is enthalpy. Before understanding the work done in the processes, let us first understand the nature of work and heat with two examples. For example, if we take a plastic bottle and if we insert a balloon to that plastic bottle. Now I am inserting this plastic bottle with a balloon in a hot water. Now what will happen here? Here the balloon is expanding after some time. Now why does the balloon is expanding? The plastic bottle absorbs the heat from the hot water and this causes the balloon to expand. Here plastic bottle and balloon is an system, whereas hot water is an surrounding. Here work is done by the system and hence work is negative here. Whereas heat is absorbed from the surrounding and hence heat is positive here. So, whenever work is done by the system, it is negative, and whenever heat is absorbed from the surrounding, it is positive. Let us consider another example. If I am taking an aluminium tin and heating it. Now, after heating the aluminium tin, I am immersing that into a cold water. Now what will happen here? Here after some time the aluminium tin burst. Now here heat is being given out to the surrounding. Now when the aluminium tin is bursting, heat is transferred to the surrounding, that is to the cold water. Hence here heat is negative. But work is done on the system by the surrounding. Here system is an aluminium tin and surrounding is a cold water. The cold water of the surrounding causes bursting of an aluminium tin which is in system and hence work is positive here. Hence whenever work is done on the system, it is positive, and whenever heat is being transferred to the surrounding, it is negative. So we can say sign conventions for heat and work are: whenever work is done on the system, it is positive. Whenever work is done by the system, it is negative. Heat absorbed, it is plus Q, and heat released, it is minus Q. Till now, we have seen the formula for the work, that is work is equal to force into displacement. It means that whenever any object undergoes displacement with a specific force, then we can say that work is done. In thermodynamic processes, the work is in the form of pressure and volume type. Now, let us see the work done in isothermal irreversible process. Consider a certain amount of a gas at constant pressure P enclosed in a cylinder fitted with a frictionless, rigid, movable piston with cross-sectional area A, as shown in the figure. Let the volume of the gas be V1 at temperature T. Here, the work can be given by the formula force into displacement. Let this equation be as equation number 1. The negative sign signifies that when the piston moves against an opposing force, the internal energy of the system doing the work will decrease. Hence, this process, work done by the gas, can be given as work is equal to minus F into D. On expansion from V1 to V2, the force exerted by the gas is F is equal to P external into A. Let this be equation number 2, whereas P external is an external atmospheric pressure. As we know that work is equal to F into D, Here we can substitute F as P external into A. So we will be getting work is equal to minus P external into A into D. Let this be equation number 3. Here A into D is change in the volume, that is delta V due to the expansion. Here delta V is V2 minus V1. Hence, from all above the equations, we can say that W is equal to minus P delta V. Hence, this is a formula for work done in an isothermal irreversible process. We have seen work done in isothermal irreversible process. Now let us see sign convention for the work with respect to the formula, that is work is equal to minus P delta V. When gas expands, work is done by the system on the surrounding. So V2 will be greater than V1. Substituting this into the formula, W is equal to minus P delta V. Delta V is positive and hence work is negative here. If gas is compressed, work is done on the system by the surrounding. Here V1 is greater than V2 and hence when we substitute into the formula, we will be getting W as positive. Whenever there is a free expansion of a gas, that is in vacuum, P external is equal to 0 and hence W will be 0 over here. Now let us see units of energy and work. Work and energy can be calculated in joules or calories, but for PV type of a work, we can calculate it in liter atmosphere or bar dm3. Hence, whenever P is in atmospheric or bar or volume is in liter or dm3, we calculate the work in liter atmosphere or bar dm3. But we can give the work and energy in joules or calories as well. Here 1 joule is equal to 1 kilogram meter square per second square, which is equal to 1 Pascal meter cube. 1 Pascal is equal to 1 kilogram per meter per second square. Also 1 bar dm cube is equal to 100 joule. We have seen work done in isothermal irreversible process. Now let us see work done in isothermal reversible process, which is also called as concept of maximum work. Work is said to be done when there is opposing force. If opposing force is 0, work is also equal to 0, which is in vacuum. If opposing force is small, work is small, and if opposing force is maximum or very close to the driving force, work is maximum. Hence, expression obtained is W is equal to minus P delta V. If pressure P of the gas differs from P external, then delta P will be equal to P minus P external. Here P external we can write it as P minus delta P. Now substituting this into the formula of W, we will be getting as W is equal to minus P external minus delta P into delta V. Hence, from this formula we can say that work will be maximum if delta P is smallest. We can obtain maximum work with the following conditions. If opposing force is infinitesimally smaller than the driving force, the work is maximum. If this is obtained, the process will be reversible. Maximum work is obtained from the change which is thermodynamically reversible. We have seen work done in isothermal irreversible process. Now let us see the expression for work done in isothermal reversible process. Consider n moles of an ideal gas enclosed in a cylinder fitted with an frictionless movable rigid piston. It is expanded isothermally and reversibly from the initial volume V1. As you could see in the figure that there are numerous weights kept on the piston. At each step, the weight is being removed. And when the weight is being removed, there is very small expansion of the gas, that is dV. At each step, the equilibrium is attained. Reversible process proceeds with an infinite number of steps. We can give work done is equal to minus P external into delta V. But small amount of work is done during very small expansion, and hence it can be given by dW is equal to minus P minus dP into dV. So let this be equation number 1. Hence dW is equal to minus P dV minus dP into dV. Multiplying dV with the bracket. Let this be equation number 2. dP and dV are extremely small, hence dP into dV will be even more small, and hence it can be neglected. Therefore, we can say that dW is equal to minus P dV. For an ideal gas, as we know, PV is equal to nRT or E is equal to nRT upon V. Substituting this value of P in the equation number 3, we get dW is equal to minus nRT upon V dV. For work done associated with a definite change in volume from V1 to V2, the above equation may be integrated as follows. Integration 0 to max dW is equal to minus nRT integration V1 to V2 dV upon V. The integration of V1 to V2 dV upon V is given as W max is equal to minus nRT log to the base E V V1 to V2. Log to the base E V V1 to V2 can be written as W max is equal to minus nRT log to the base E V2 minus log to the base E V1. Now this log to the base E V2 minus log to the base E V1 can be written as W max is equal to minus nRT log to the base E V2 upon V1. Converting natural log to the base E to log to the base 10, we will be getting as multiplying with 2.303. W max is equal to minus 2.303 nRT log to the base 10 V2 upon V1. According to the Boyle's law, P1 V1 is equal to P2 V2 or P1 upon P2 is equal to V2 upon V1. Hence, substituting P1 upon P2 in place of V2 upon V1, we can give the equation for the W max as minus 2.303 nRT log to the base 10 P1 upon P2. So these both the equations are the expression for work done in isothermal reversible process or work done obtained in maximum work. We have seen the expression for work done in isothermal irreversible process and isothermal reversible process. Now, let us see first law of thermodynamics, which can be said as modified form of a thermodynamics law. Now, we know according to the Einstein equation, E is equal to mc square. In the above equation, energy E is equal to the matter m, which is m times square to the constant c. Einstein suggested that energy and matter are interchangeable. His equation also suggests that quantity of energy and matter in the universe is fixed. Hence, according to this, we can say that total mass and energy of an isolated system remains constant. And this is what is first law of thermodynamics. The corollary for the first law of thermodynamics is there is an exact equivalence between heat and mechanical work. We have seen the statement for the first law of thermodynamics, that is, energy can neither be created nor destroyed, although it may be converted from one form to another. Now, let's formulate the first law of thermodynamics. A system exchanges energy with its surrounding, either by transfer the heat by doing work. And energy supplied to the system, it increases its internal energy. On the other hand, when we remove the heat, it decreases the internal energy of the system. Supposing Q is an heat supplied to do the work from the surrounding. Hence, internal energy of the system will also increase. Increase in the internal energy of the system is equal to sum of the quantity of the heat supplied to the system and amount of work done on the system. Hence, we can formulate the expression for the internal energy as delta U is equal to Q plus W. Let this be equation number 1, where delta U is increase in the internal energy of the system. Hence, the first law of thermodynamics, when it is an infinitesimal change, can be given as du is equal to dq plus dw. Applying first law of thermodynamics to different types of process, let us first see isothermal process. In isothermal process, temperature is constant, hence delta T is equal to 0 and delta U is also equal to 0. Here Q is not equal to 0. Now the system can be either open system or closed system. According to first law of thermodynamics, delta U is equal to Q plus W. So, substituting delta U is equal to 0, we will be getting Q is equal to minus W. Hence, we can say that the heat absorbed by the system is entirely used for doing work on the surrounding. When work is done on the system by the surrounding, it results to release in heat. Now, let us see another process, that is an adiabatic process. In adiabatic process, temperature varies. That is, delta T is not equal to 0. Delta U is also not equal to 0. Whereas, heat is constant and hence Q is equal to 0. Now, this process usually occurs in isolated type of system. So, according to the first law of thermodynamics, delta U is equal to Q plus W. Here, delta U will be equal to W since Q is equal to 0. Now, let us see another process, that is an isochoric process. In isochoric process, volume is constant, delta V is equal to 0. Now, considering the equation W is equal to P delta V and replacing P with the P external and Q with the QV, we will be getting the delta U will be equal to QV plus W. Since delta V is equal to 0 and P external into 0 will be equal to 0, hence W will be equal to 0. Hence, it shows that the change in internal energy of the system is due to heat transfer at constant volume. The subscript V indicates that heat is transferred at the constant volume. Further, U being a state function, QV is also a state function. Let's see another process now, isobaric process. In isobaric process, pressure is constant. Hence, delta P will be equal to 0. Here, delta U will be equal to QP plus W. Since delta P is equal to 0, hence we will be getting delta U is equal to Q. Let us now see a very important concept, that is an enthalpy. Enthalpy of a system is also called as a heat content of the system. It is a thermodynamic function used to describe heat energy changes in chemical reactions taking place at constant pressure. Hence, we can define enthalpy as the total energy content of the system inclusive of pressure volume type of energy. Enthalpy change at constant pressure, whenever we have to calculate it, we can give by the equation H is equal to U plus PV. Since the absolute value of enthalpy of a system cannot be determined and it is also not significant, the change in enthalpy, that is a delta H, can be determined. So here we consider the change in enthalpy, that is delta H, and delta H is equal to H2 minus H1, whereas H1 and H2 are final and initial enthalpies. So we can consider H2 is equal to U2 plus P2 V2 and H1 is equal to U1 plus P1 V1. Since delta H is equal to H2 minus H1, which is a final minus initial, substituting the values of H2 and H1 in the equation. Let this be equation number 1. Most of the processes are carried out at atmospheric pressure. Hence, P1 will be equal to P2, that is equal to P. So, we can say that delta H is equal to U2 minus U1 plus PV2 minus PV1. So, finally, we will be getting the equation as delta H is equal to delta U plus P delta V. So, your total energy content of the system inclusive of pressure volume type of energy. Mathematically, the equation for the enthalpy can be given as H is equal to U plus PV. Since P and V and U are the state function and hence enthalpy is also a state function. Let us now see the expression for the enthalpy change at constant volume. At constant pressure, delta H is equal to delta U plus P delta V. So, at constant volume, delta V will be equal to 0. So, the equation for the enthalpy, delta H will be equal to delta U. According to the first law of thermodynamics, delta U is equal to Q minus P delta V. So, your Q will be equal to delta U plus P delta V. So, QV will be equal to delta U. Since P delta V, if it is equal to 0, so QV will be equal to delta U. Hence, from both the equations, that is from equation number 1 and 2, we will be getting delta H will be equal to delta U, that is equal to QV. Let us now see the expression for the enthalpy change for the gaseous reactions. As we know that delta H is equal to delta U plus P delta V. But P delta V is equal to P into V2 minus V1, which is equal to PV2 minus PV1. Your V2 is the volume of gaseous product and V1 is the volume of gaseous reactants. For an ideal gas, PV is equal to nRT. So PV1 will be equal to N1RT and PV2 will be equal to N2RT. Hence, PV2 minus PV1 will be equal to N2RT minus N1RT, which is equal to N2 minus N1 into RT. And hence, we will be getting the equation as delta H is equal to delta U plus delta N RT, where delta N is for the gaseous and hence we will be writing as delta H is equal to delta U plus delta N G R T. Thank you for listening patiently. In the next video, we will be studying about the enthalpy changes in physical transformation.